Welcome to this revision zone video. I'll be looking at using quadratic equations to solve Kp expressions, more specifically calculating equilibrium moles at a specific temperature and pressure. Now there's two examples I'm going to look at here. The first one you can see in this question, it does say you don't need a quadratic equation to solve it. So I'll be showing you that route, and I'll also be showing you the route of using a quadratic equation to actually solve this. Now, the question says calculate the number of moles of each species at equilibrium if you have 0.5 moles of A and 0.5 moles of B and are mixed at 500 Kelvin, a constant temperature and pressure, and the Kp is given at equilibrium as well, which is going to be important. So, first of all, we've got our reaction, our system. Essentially, we're going to use an ICE table, which you may have used at school or may have been referred to as ICE. So we put the initial, the difference, and then the equilibrium moles within a table. I don't tend to use that. I just tend to go initial moles, and write those down. So those are my initial moles straight from the question. So we've got 0.5 moles, 0.5 moles, and these are reactants which have been told or given to us by the question itself. But in regards to products, we don't have any. So our initial moles of products is going to be 0. I then say, well, for A and B, my reactants, they are going to reduce by the same amount because it's a 1-to-1 ratio. It's a 1-to-1 ratio from the stoichiometry in the equation itself. So I know that they are going to reduce by X. Okay. And then with C, because it's a 1-to-1-to-2 ratio, C is going to go up by 2 lots of X. So if I was to simplify this, if we just use the term 1 mole for X, so this A will reduce by 1 mole, for instance, B will reduce by 1 mole, and if they were to reduce by 1 mole, 2 lots of C will increase by 2 moles. So we see that next, and we're going to represent that change by using X, and we can see that on these arrows. Always worth writing these down just so that you can visualize what's going on. I then write this expression for each equilibrium moles of A, B, and C. So once I do that, I have 0.5 minus X, which is this moles is reduced by a number, and we're going to call it X. Okay, and we're going to do the same for B. So we end up with these two exact same terms, and zeros added to X, so that just becomes 2X. Now, like I said, I'm going to show you two routes in doing this. The first route is not needing a quadratic equation, and the second route is, route 1. So if we look at route 1, we're going to write the Kp expression for A, B, and C, which is shown as follows. So Kp is the partial pressure of C squared over the partial pressure of A times the partial pressure of B. Next, we're going to just sub in these values we have at the bottom from our equilibrium moles. So we're going to do that, and we end up with the following. So 2x is all squared because it will be this term here squared due to this expression here. And at the bottom, 0.5 minus x times 0.5 minus x, which essentially is just 0.5 minus x squared. So I've written it as so. And that is all equal to 2.5 because our question gave us the Kp at 2.5. So we're just equating that to Kp. Now, instead of going down a quadratic route and trying to solve this via that route, we can just take the square root of both sides because both numerator and denominator are squared. So if I square root that, I essentially get rid of the squareds. And then I square root 2.5. So whatever you do to one side, you must do to the other. We end up doing that. And we get the square root of this term and the square root of 2.5, this term being this term here, and 2.5. That leaves us with the following expression. We can see the square terms have not disappeared or removed, and the square root of 2.55 is 1.597. We're then going to rearrange this. So I'm going to move the denominator, that term, over to the right hand side. By doing that, I'm going to multiply. That leaves me with this expression here, 1.597 outside the brackets times the 0.5 minus x is equal to 2x. Once I expand that bracket, I end up with the following term, or the following expression. And now I'm going to simply rearrange this to get x onto one side, and then solve x. So I end up with 3.597, x is equal to 0.798. I rearrange that, so I divide by 3.597, and that gives me that, and x as follows is 0.222. You could have quoted this to two significant figures, and I would probably expect you to do that because that's what they were given as part of the question. Although it does have 2.55 here, so we can still quote it to three significant figures, and it's fine. I'm then going to use that, and I'll show you this later, to work out the equilibrium moles. What I would like to do is focus on both methods. So root 2. Now root 2 will look at solving this using a quadratic expression, or the rule. So this is root 2. We're going to start with the same expression as we did over here, so we know how we got to here, so we're just going to use this again, and that is here. And then we're going to expand each of these brackets, top and bottom, numerator and denominator. This is the long route of doing this particular question, but I just want to show that you get the same answer. So if we expand, we get these terms, 4x squared over 0.25 minus x plus x squared, that's equal to 2.5. I'm then going to again do very similar to what I did on the right hand side, move my denominator over, and that gives me 4x squared is equal to 2.55 times the term in the brackets we've got here. Once I've done that and expanded that, I end up with the following term. So 4x squared is equal to 0.6375 minus 2.55x plus 2.55x squared. So we've just expanded those brackets there. What we're then going to do is we're going to rearrange this. Now we want to keep our x squared positive, so I'm going to move everything over to the left. I end up with 1.45x squared plus 2.55x minus 0.6375. Now it's at this point we use our rule or quadratic equation to solve x. Now we know that this term is a, this bit here, this is b, and this is c. So we're just going to input it into the equation as follows. So we know this expression, or we should know this expression. We're just going to input all the values, b being 2.55, a being 1.45, c being 0.6375, and then divide that by two lots of a. So we're just going to input that all in, and we should get the following, which we do. And this is, I've just worked out what b squared and 4a minus 4ac is, and it ends up with actually a positive term there in the end, and I'm going to divide that by 2.9. What I've then done is I've just shown what the total value is inside this square root, which is 10.2, just for simplicity. Now I've got a plus and minus term, so I need to work out the two solutions for x, and I end up with two solutions. One's going to be positive, one's going to be negative. The negative one here is not what we're going to use. The number of moles has to be between, well, it has to be above 0. It can't be below 0. So we're not going to use this one here. So our final answer for, oh, not a final answer, but a change in moles is 0.222, which is exactly the same as what we had above. So we've proven that we've just got the same answer by using a different route. Now, irrelevant on which route you go, you end up with the same answer, obviously. We're just going to input that 0.22 and sub it in for x over here. So what we end up with, just going to end up writing that same ice table, if that's what you want to call it, initial moles, but this time I've subbed in x minus 0.222, and again, and for c, I am actually going to add two lots of 0.222, and that leaves me with the following, and this would be my final answer. Each of these would be my equilibrium moles. So if we just highlight those, there we go. 0.722 for A and B. They both started at 0.5, remember, and you're going to take away the same number of moles, whereas the number of moles of C at equilibrium will be 0.444. Again, you could quote that to two significant figures. So I hope those made sense, root 1 and 2. It's definitely worth looking out for this, the ability to do this, square root both sides. So on to the next question. In this question, we're not going to be able to just square root both sides of our equation. We're actually going to have to use a quadratic equation to solve this question. And it says that here. So in this particular one, calculate the number of moles of each species at equilibrium when you've got 5.00 moles of CO2 and 1.00 moles of H2 are mixed at 1000 Kelvin. Again, it's the same temperature and pressure, it's constant throughout, with a Kp at 0.72. So here's our system. CO2 plus H2 gives us carbon monoxide and steam. So I'm going to again draw a nice table. So remember, that's initial, change and equilibrium. I don't quite write ice down the side. I just write initial and equilibrium moles, as I mentioned before. So I'm going to start off with the equation. And I'm going to show you the whole lot. So this is no different to what we looked at before. So I'm just putting the initial number of moles of each component at the top. It's 5 moles as stated by the question and 1 mole as again stated by the question. And the products always start off at 0. Well, not always, but in this case they do, because they haven't mentioned the number of moles of any product initially put in. Now, because it's balanced and it's a 1-to-1 to 1-to-1 ratio throughout, they will all reduce or increase by the same magnitude. So we know that reactants will go down, so minus x, and products will go up by plus x and plus x again. So when we look at equilibrium moles, we're going to use that x and the initial number of moles to work out the equilibrium moles in terms of x. So what we've got here is 5 moles minus x, 1 mole minus x moles, and x moles and x moles. So these are essentially the same. So again, we're going to put it into our Kp expression. Now we know Kp is 0.72 from the question above, and that's our Kp expression. Remember, it's always the partial pressure of products over reactants. Then we insert our terms at equilibrium moles, so 5 minus x, 1 minus x, and x, and we get this term. I'm sure you know all this, but it's worth just going through it. X times x, obviously x squared. I expand the bottom denominator there, and I end up with this expression here, and that is all equal to 0.72. Again, I'm going to move the denominator over to the right hand side, so I'm going to multiply 0.72 by the denominator, and I will need to expand that. So once I've got that there, you can see that I've just moved that bottom denominator term over, and I expand it. I get the following: 3.6 minus 4.32x plus 0.72x squared is equal to x squared. So I want to keep my x squared term positive, so I'm going to move everything over to the right hand side. When I do that, I end up with 0.28x squared plus 4.32x minus 3.6. I now again have my algebraic expression where I have a, b, and c, and I'm just going to use that a quadratic equation to solve this now, exactly how we did before. So let's have a look at that. So first of all, let's write down a quadratic equation. There it is: minus b plus or minus square root of b squared minus 4ac divided by 2a. I'm going to insert all my values from here into this expression here, same as before. And I've done it like so. I've already worked out the b squared and 4ac as before. And I've just worked out the term inside the square root, which is that. So then I'm just going to work that out. I'm going to work out both terms. I'm going to obviously get a positive and a minus x here. Remember, the number of moles must be above 0. It must be a positive value. It can't be a negative value. And the two terms I end up with here is 0.793 and minus 16.22, which I'm definitely not going to use because the moles can't be negative, the final equilibrium moles. It's got to be greater than 0. So this here is my value for x. So I'm going to go back to my ice table and I'm going to insert the value of x into each of these expressions. Now for these two here, it's quite straightforward. They're going to be 0.793 each because they are equal to x. I just need to go 5 minus 0.793 on each of these. So 5 minus that and 1 minus x. And I end up with the following equilibrium moles. Now, if you wanted to check that you were correct or you were right, if you inserted each of these equilibrium moles into your Kp expression up here, you should end up with 0.72. Now, if it's an exam situation, I would only do that if I had the time. So that concludes us looking at the two questions that I would expect you to probably see. And the approach is always the same. It's one of the two approaches we've looked at in this video. I hope it was useful. If you found this video useful, please hit the subscribe and hit the like button for us to support our videos, and we will hopefully see you in the rest of the videos.